Let's take a look at instantaneous rate of change. Let's start just by drawing a generic graph. Let's say we're graphing y equals f of x. And let's maybe identify tangent lines to this particular function at a couple of different points. So the slope of these tangent lines are given by f prime of x, our derivative. And f prime of x actually represents two different important quantities to us. It represents the slope of the tangent line, which we're familiar with by now, and it also represents what's called the instantaneous rate of change. Of our function f of x. So the derivative tells us how quickly f of x is increasing or decreasing. If we go up to our sketch here, you can see at this point where the slope of the tangent line is positive, that corresponds to the function increasing. The y values here are increasing. And over at this second point where the slope is negative, slope of the tangent line is negative, that corresponds to the y values decreasing, or the function decreasing. So instantaneous rate of change of a function tells us about how quickly the function itself is increasing or decreasing. So let's try a little example here. Let's say we have a function v, which looks like 4/3 pi r cubed. So you might recognize that as the volume of a sphere with radius r. Well, in this problem, we're going to find the instantaneous rate of change. Oops, instantaneous, always a tricky word to spell. The instantaneous rate of change of our function v with respect to r. And let's do that at the moment when r is equal to 2 centimeters. Okay, and that way we've got some units there. So to get started on this problem, we just need to recognize that instantaneous rate of change is just another way of referring to the derivative. So what we're really looking for is the derivative of our function v, derivative of v with respect to r. So we write that as dv by dr. Okay, now we can take our derivative. The 4/3 pi, it's just a coefficient out in front here, so we'll leave that coefficient alone, and we'll multiply by the derivative of r cubed, which is going to be 3r squared. So if we simplify this, it looks like 4 pi r squared. So this is the instantaneous rate of change of v with respect to r at any particular r value. Now in the question, we're asked to find this quantity when r is equal to 2. So now that we've found our derivative, we actually need to calculate dv by dr evaluated at r equal 2. So in other words, we're just going to plug in r equal 2 into this formula here and see what we get. So we'd have 4 pi times 2 squared, or in other words, 16 pi. Now, we did have some units given in this problem. Remember, r here was measured in centimeters. So when we give the units for the rate of change, we're actually going to give it as a fraction, Okay, the denominator of the fraction is going to be centimeters because that corresponds to the units of R. And the numerator for the units is going to be whatever the units of V is. Well, if we think about volume here, volume is measured in R cubed. So if R is measured in centimeters, then volume is going to come out centimeters cubed. So initially this looks a little bit weird, centimeters cubed over centimeter. But there is actually a physical meaning to these units. What this is saying is that at the moment when R is equal to 2 centimeters, every centimeter of change in R corresponds to 16 pi cubic centimeter change in the volume. So for every centimeter gain in R, you gain 16 pi centimeters cubed in the volume at the point when R is equal to 2 centimeters. So it's actually more meaningful to leave the units like this and not simplify that fraction in any way. So the trick for remembering the units, the numerator is just going to be the units of whatever your initial function is, v in this case, and the denominator here will be the units of your variable, which appears in the denominator when you write the derivative this way. So in this case, it's the units of R. Now to continue our discussion, we want to look for a second at the idea of higher derivatives. And then we can go on to a nice application. So let's say we take a function f of x, just a nice polynomial. Maybe it's 8x cubed minus 5x. And we know from our derivative rules that f prime of x is going to look like 24x squared minus 5. And we can continue taking derivatives. So the next thing we would write down is f double prime of x, or we might also call that the second derivative of f. And this just represents the derivative of f prime of x. So we're just taking the derivative of the previous step. So if we take another derivative, we get now 48x. And we could continue in this way. Could even find the third derivative, f triple prime of x would be 48. At some point it gets pretty annoying to put all these little prime signs there, so you could even write third derivative of f. That becomes more common as we move into higher derivatives. So third derivative of f is 48. Now let's take a look at an application of higher derivatives. Imagine that we have an object and it's moving in a straight line. Object moving in a straight line. So starting at this position, and it can move along this line, either in a forwards or backwards direction. So let's let s of t represent the displacement of this object after t seconds. Okay, and that displacement will be measured in meters. V of t is what we get when we take the derivative of s with respect to t, and that represents the object's velocity. After t seconds, velocity will be measured in meters per second. And then finally we've got a of t, which is the derivative of our function v with respect to t. Well, v itself is already a derivative of s, so we could rephrase this as saying, well, same thing as saying second derivative of s with respect to t. And this represents the object's acceleration. Again, the acceleration after t seconds. So our acceleration will be measured in meters per second squared. So let's try a little example here. First of all, we need to know that we have an object moving in a straight line. Okay, we'll look at other types of motion later on in the course. And let's say that we know the object's displacement. S of t is 4t squared plus 3t. And let's say S of t is measured in meters and t is measured in seconds. So we've got a specific displacement in meters after t seconds. Okay, the problem here is to find the object's velocity. Let's do that after, say, 3 seconds. And let's also find the object's acceleration. And let's do that after 2 seconds. So here's a good example of using higher derivatives. So in fact, what we're doing in this problem, by finding velocity, what we're doing is finding the instantaneous rate of change of displacement. So how quickly is the displacement changing? And then by looking at acceleration, we're looking at the instantaneous rate of change of velocity. So we're figuring out now how quickly is the velocity changing when we calculate acceleration. All right, so let's get going with our velocity function. Remember, velocity is the derivative of displacement. So we'll go ahead and take our derivative here. We'd have 8t plus 3. Okay, and while we're on the theme of taking derivatives, let's go on to calculate the acceleration. Acceleration is the derivative of velocity. So if we take derivative of v, we've now got just 8. So to solve the problem then, we want the velocity after 3 seconds. We'll go back to our velocity function here and plug in t equal 3. Okay, that gives us 27. And in this type of problem, because the units, meters and seconds, were stated in the problem, we should include units in our answer. Velocity is going to be measured in meters per second. And we would like the acceleration after 2 seconds as well. If we go back to our acceleration function, notice that there's no t in this function, meaning in this particular example, acceleration is constant. It's just always going to be 8 meters per second squared. Does not matter what value of time we're plugging in. So 8 meters per second squared would be our acceleration after 2 seconds.